I hope you all had a good lunch, but that should not be an excuse to. Okay, yeah. So I will. So this is mostly a superficial like a lecture where I'll be giving you an idea about how the astronomical instrumentation is done. Of course, I cannot give you all the details in 1 hour, but I'll just give you a glimpse of things that are happening. So here I'll be covering ultraviolet, optical, and infrared. Now, astronomy can be divided observation wise. We can divide it into wavelengths, basically because of the the constraints that are coming from the instrumentation itself. Okay, so when we say ultraviolet, can you tell me a ground based telescope which is dedicated for ultraviolet? Any ultraviolet telescope? You cannot have, no, because if you can have a telescope on the ground, that means ultraviolet should come to you, and that should not be right. So it should be, so you cannot. So that means atmosphere has a cutoff at 300 nanometers. It's a strong cutoff. That's why you say you cannot do. So ground base means okay, 300 nanometer. That's the cutoff that you can put for for the observations. Now coming to infrared, there are certain detectors that are used which we will discuss, and these detectors cannot detect photons which are having wavelength longer than say 1 micron. So that is the cutoff at infrared. Okay, beyond which the technology to detect these will change. So I am Maheswar Gopinathan. I work in Indian Institute of Astrophysics. So after this talk, if you have any questions, queries, you can take down my email and write to me. Okay, so I think you might have seen this image. This is basically the multi-wavelength image of the galactic plane, basically, right? Now so all these information is important to basically make some sense out of what we are looking at, because they all represent certain processes which are important for understanding things as a whole. So we will be dealing mostly with near infrared, optical, and UV, which is very close to X-rays. We are not going into X-rays. So you can see a stark difference, right? In optical you have these dark lanes, whereas if you go to infrared, they all become bright, isn't it? So infrared is not so optical, you are not actually seeing longer distances because of the extinction, because the light that is, so these are dark basically because there are bright sources, but something is sitting in between those bright sources and you, which is actually absorbing things. We'll see that. The best example is this called Bernard 68, is also called kidney shaped cloud because it's shape of a kidney, right? You can see that if you look at 0.4 micron, that is in bluer region of your wavelength, you see it as a dark thing. And initially people thought that these are like holes in the sky, right? Holes in the sky, because you're not seeing anything behind. But then if you progressively increase the wavelength of your observation, like 0.5, 0.9, you are in the infrared regime, which is 1.25, 1.65. When you come to 2 micron, your cloud is actually invisible, right? Have you heard about a invisible tower in Korea? There is a tower which is invisible. Why? Because it has cameras kept behind which takes image of the background and beam it onto the tower. So you basically see the background, right? So you feel that the tower is invisible. You can check that. So here also it's like the cloud is invisible now. Now what is happening? What is happening is the material which is present inside this cloud is actually of the size of the wavelength that you are looking at, right? So as the wavelength becomes longer and longer, it is not interacting with the material. So this radiation is coming through. So you're not seeing the cloud. So you see, if you're observing only in optical, you say that, okay, there is a dark patch. But if you go into the infrared, right, now you go to the, emission, because these are material present there which is at a temperature of about 100 to 200 Kelvin or even smaller as you go to middle part, and you see them in emission, right? So the same cloud which is absorbing is actually emitting in longer wavelength. And this cloud is not only particles, but these are gas. So it's like, so we say interstellar dust and gas present there. Now gas is basically, you know, the most abundant, you know, what is the most abundant atomic, you know, element? Hydrogen. What about molecule? Hydrogen molecule, right? But there is a problem. Hydrogen molecule you cannot detect directly. They are homonuclear, right? So they don't have a permanent dipole moment. So what you do, you use the second most abundant molecule, which is the carbon monoxide. So when they are in thermal equilibrium, you can actually see what is the, you know, the distribution of the gas in the cloud. Okay. So you see the what I am trying to tell you is that you need a multi-wavelength, you know, picture to basically make, you know, figure out things which are happening here. Now, these are the clouds where stars form. Okay, these are the cores where star formation happens. So these are very important. Now, you know, if you look at, so the definition for the UV-OIR is that, you know, so the shortest wavelength that you can go in UV is 912. What is the, you know, speciality of this 912 angstrom? Think about it. Okay, I'm leaving it to you. And the longest wavelength that we can have in infrared is about 3 micron, 1 to 3 micron. Okay, now that's basically because, you know, you look at this figure. Okay, now at 300 nanometer or 0.3 micron, this the absorption is quite high. So the sky is not going to permit those radiation to pass through the atmosphere, right? If you and you see the optical, which is up to 1 micron, it is fairly transparent, isn't it? So you can, that's why you are observing everything, right? But if you go to the infrared, there are these bands. You know, the most important, you know, the most, you know, the absorption, the factor which absorbs the radiation that is coming is basically the water vapor content in the atmosphere, and, you know, and the carbon dioxide. So if I ask you which would be the best observing site for infrared wavelength, region which is like this or dry? You need dry, right? So that is why we have our you know, observatory in Hanley, which is the highest, right? That's quite dry place, and it's fantastic for infrared. You go to Hawaii, which is the best site for observation, you know, astronomical observation. Again, it's dry, right? And you know this, right? This happens to fall in the optical regime, basically, which actually gives you the H alpha, you know, the Balmer, which is the most prominent line in Balmer series, H alpha, then H beta, right? Okay, so these are basically the main observational things that we carry out in this wavelength regime. You do imaging, you do astronomy, you do you know, astrometry, you do spectral energy distribution. For that you need to have photometry and spectroscopy, and then you look for variability, and you actually look for the polarization in these radiations. Now, why? The only information that you are getting from these, you know, these astronomical objects are basically the radiation, right? So you have to make best use of it. Either you take the images to see the orientation or the extended structure in them, or you see the elemental presence in these, you know, these stars. Now, why is it that the, you know, optical wavelength regime is important? You know, the gamma ray burst sources were first detected in 1970. Now, you cannot actually pinpoint to us, you know, what actually is the source of this gamma ray burst until you you get to associate it with an optical source. Why? Because once you associate an optical source with it, you can actually get the redshift, and you can find the distance to that source, provided some of your assumptions are correct. Okay, but you can get the distance of the source, and you can actually do many things like cosmological importance of that source, so on and so forth. So astronomy is driven mostly by observations, right? And that observations actually dictate how the theoretical things move. But there are certain things where theory came first and then observations were followed up, basically. Okay, for example, the stellar evolution, which is well established in the theoretical ground, and observations were made in the subsequent. So this actually is a long list of things that you can actually, the processes that you can understand if you have this observations, right? And now the theory driven discoveries are like the presence of Neptune, 21 centimeter line, right? You might have had some lecture on 21 and then the helioseismology. So theories came first, but there are certain observations which are basically accidental, right? Cosmic microwave background, isn't it? So this actually gives you an idea of how things move in astronomy, basically. Okay, now all astronomers, be it you are doing theory, you are doing observations, instrumentation, you should have some feeling about the data that you are getting. What's meaningful data? Okay, what's not, what's real, what is noise, the systematic errors, what are the signals that are interesting to you. All these things should be known to you, because that then only you will understand answers to some of these questions. For example, this is the HR diagram. Heard about HR diagram? Hertzsprung diagram. Now you see it's a well polished, the figure. People say, yeah, we understand everything, but when the Gaia color magnitude diagram was made, what objects represent this region? These are white dwarfs. Okay, so white dwarfs come here, and if you closely look at, there are two sequences. Why there are these two sequences? Is it that we are missing something? Is it their observations are wrong? What are they? If you want to understand this, you have to see the data that you're getting, right? There is a huge scatter here, right? I mean, I would have expected everything to follow, very tight correlation, but is it because of the binary, or is it because of a difference in the metallicity in the stars? Are they not the similar kind that you're looking at? Some of the things which, you really have to look at, if you can do only if you know what is the kind of data that you're looking at. Now, one startling thing that you might have noticed here is that this figure is not fully occupied. Why? Say here, these are basically low mass stars, right? That means they should, after going up, they should come like the planetary nebulae stage and then come to the white dwarf. You don't see them. You see mostly, these are basically because they spend most of the time there, right? The other evolutions are so fast that you're not actually picking them on the chart diagram. Okay, this I'm just skipping. So the ultraviolet region is basically rich in atomic, lines, transitions. So if you want to study, for example, say the high temperature gas, you need to go into these, because these are like highly ionized gas emission which comes in the ultraviolet. And of course, optical is very rich. So this you know about this. O, B, A, F, G, K, M. These are the classification of the stars, and you see, you come to A0 type, which is 10,000 Kelvin, No, this is H alpha. So this is basically the, so A type is where the, the brightest, it is brightest in H alpha, right? So the Balmer, so these are basically the Balmer lines that you see. Most of the Balmer lines, you can see it on the hotter stars, the massive stars basically. Okay, and the cooler ones, what are these? Because they're cooler, the atmosphere is cooler, so they give you bands, molecular bands. So these cooler stars are rich in molecular bands, and the high mass stars, as you go, they are actually very, so the absorption in the Balmer lines are quite high, and then if you go to very high, you can even see the helium lines. So okay, so if you're there is something called habitable zone. Okay, habitable zone is the region where the water can survive, and that region is closer to low mass. Huh? Absolutely. So they are closer to the star. So what is the spectral type of sun? Hmm? G2, right? Yeah, G2. Where is the life? At what distance? 1 AU. Right? So you see G-type stars 1 AU. If you go to cooler stars, it will come closer and closer. So technically, it will be difficult to find say planets near low mass stars because they are very close to, I mean the Earth-like planets, because they will be closer to the star, right? The other one, the star itself is so bright that you won't be able to see the planets which are there. So you have to use the technique. So it's not easy. So the best way to do is radial velocity. We'll come to that. Yeah, so this is basically the radial velocity curve. So what happens is if you have a star and a planet, as they go around about center of mass, yeah, so what happens when they go around? Two things go around. This is coming towards you, this is going away. So what this will give? A line which will be blue shifted. What will happen to this? Red shifted. Now ulta, it goes away, this goes down. So this is like, this will be modulated by the rotation period. So you can actually find if there is some component there, right? Now this is a Nobel Prize work. What it actually does is the motion of stars around black hole in our galaxy. So they traced, I think it's a 20 years of data, painstaking data taken to basically look at the orbits of the stars around on the black hole, and you model it and see what is the mass of the black hole at the center, right? So you have to keep looking at the astrometry of the stars, how the stars are moving, right? At some point, stars will not be stars because they will be disrupted. So these are actually far away stars which are really going around, because of the presence of a massive counterpart there. So this is astrometry at its best. Now you look at here the spectrum. This is a normal spectrum of a galaxy or a star, basically with no redshift. But as the redshift, you go to higher and higher redshift, this line, the emission line, will move, right? So the Balmer line, which is the H alpha line, 6563 angstrom, will actually move, right? And you can find out how much is the distance with certain certain assumptions. And this, can you guess what this is? Is a light detecting planets. So what is, so if there is nothing, so something is going in front of it, right, blocking the light. So you get so you really require signal to noise. The ratio, signal to noise ratio, should be high. Just see, can you make out? Nothing, right? So here little bit more, but you come to here, it's very clear. So you can actually find out what is the diameter of the planet, of the star itself. And if you can actually find out what is the slope of this, you can find out what is the size of the planet itself, right? So this is, the importance of, observations. Can anybody guess this? This is a photograph taken over a year, maybe, of the sun, right? So sun can go up to how much? 23 and a half, 23 and a half, right? Tropic of Cancer, the other side is Tropic of Capricorn, then it comes down basically, right? So you take a photo, take a camera, put it over for your sun, take the, every day you click the picture, actually you can see this. So this is basically for a latitude of 19. Okay, so this you must be, when the earth goes round, your sun will be in different constellations, right? So birth signs are basically said like that. So when you're born, where is the sun, in which constellation it is? So that's how people say. So this is basically the ecliptic plane, where the sun goes through certain constellations, and so there's another view of the same thing. Okay, anybody is in Aries sun? You don't want to reveal it, it's okay. Okay, so this is basically so you all see stars, right? But you have to pinpoint them in the sky, because if you want to tell somebody else that I have seen this star, this is the coordinate, basically like Google Earth, you have all the coordinates fixed, right? If you want to do it for the stars, what you do is basically, if this is the Earth, right? You are standing like this, right? You will be along the radial, and this will be the celestial, the horizon basically. So I hope you can see here. So if you say, basically define this as your horizon. Horizon is the extent over which you can see the objects, right? And then you are at the middle, right? And then this is your celestial sphere, right? This is called zenith, right? Now if you're standing on equator, how will the stars move? Okay, let me ask this question. If you are standing on the equator, where will be the North Pole? If you are on the, very good, on the horizon, right? Isn't it? North Pole is on the horizon. So it will be somewhere here, right? Now, if you take a photograph with North Pole at the center, what will you see? Stars rotating around. So here what will you see? See them going around, right? Isn't it? Going around. What will happen if you are on the North Pole? Where will be the North Pole? Zenith is the North Pole. So the stars will all go around, right? Now if I take a general, so that means if you are on the equator, means what is your latitude? 0. And where is your North Pole? No, you say you start from the horizon. Angle is measured from the horizon. So it is 0, right? When you are on the North Pole, what is your latitude? 90. Where is your North Pole? 90, right? That means there is some connection between the North Pole and the latitude. So here the latitude is about 12 degree. Where would I see the North Pole? 12 degree from the horizon, right? So I say somewhere here, this is my latitude, 12 degree, this is the North Pole, so I am here, right? Isn't it? The North Pole. So this is the North Pole. Now stars will go round. After a certain point, so till somewhere you can see them going round, but after some time they just rises and sets. The ones which are going around are called the circumpolar stars, right? The others will just go around. So where will be my so there is something called right ascension and declination, right? Now can you tell me how sun moves on the earth's surface, say on March 21st? Yeah, it goes around, it is on the equator, right? That is why you have uh, the earth, the night and the day equal, right? Now so what happens on say March, April, May, June 21st? Tropic of Cancer, it again goes around in a circle, right? June, July, August, September on the equator. October, November, December, it's down, right? So every day if you look at it, it takes a circle, right? But over a year how it will move? Tropic of Capricorn to Tropic of Cancer. So it moves like that, right? So the point, so this is called the ecliptic plane, okay, where the sun moves over a year, right? So the point where ecliptic plane intercepts the equator, that is the first point of Aries. That is where you define your right ascension as 0, okay? Then you increase it to other values, okay? So let me ask you this question. What is the right ascension of sun on March 21st? How many say 0? Why it is not 0? So that is, so the point where ecliptic plane and equator intersects is the 0 RA, right? That is the point we say 0. That means sun, what sun is doing on that day? It is on the equator, right? Isn't it? No, that depends on the place actually. Okay, so basically it is so RA is 0 on that day, and every month RA increases by 2 hours. Why? Because it has to cover 360 degrees in 1 year, right? So every year, so that means March 21st the sun's RA is 0. What about April? In hours. You are saying in degree. 2 hours added. 2 hours, right? So you can actually find out by given the month what is the RA of the sun. Can you tell me the RA of sun today? May. Yeah. So March, April, May, 4 hours, right? Yeah. Now I'm an astronomer. I go to observatory. I want to observe a star which is, so this is 4, right? So I want to observe a 10-hour star. You know, hours increases as you go towards east from west. Okay. So let's say, I don't know which is east or west here. So let's say this is east, or this is east, this is west. Okay. Now if at evening at 6 o'clock on March 21st, what will be the RA of the star in my zenith? RA increases from west to east. So that means it increases from here, right? On March 21st, what is the RA of sun? 0. What will be at my zenith? Twelve is half, right? 24 is one full, 6 hours. So it will be 6 hours. So I don't have to say anything. I have to just look at the month. Okay, I have to fix what is the RA of the sun. I know where the sun is in the evening. I know what is the star which is transiting at my zenith. So that's how you can actually. So basically um, you can find out what is the RA, and so this means that your zero declination is basically from the North Pole to say the celestial equator. So this is horizon local to you, but this is the celestial equator. Okay, so if a star is here, the declination will be this, where this is 0 declination, this is 90 declination, and this other side is minus 90 declination. So that is how the declination. So you have RA, you have declination, so you have two coordinates basically to fix the position of the star in the sky, right? Now any star which is, so this is the declination basically. Now this is your zenith, right? And this distance is called zenith distance. It's very important because I'll tell you here why it is very important. So this you can keep in mind what is the zenith distance, right? So a fun question. So if I take a photograph of the star trails, where I have taken the photograph this from and this from, is it the latitude, which is latitude 0 and which is latitude 90? Very good. So this is 0 because it's on the horizon, right? You can try if you have a camera, a clear night. Don't try it in the metros on cities. Go to a village or somewhere where no light pollution and try this. Okay, so I think you all know about the stellar parallax, right? Is basically the way in which you can find distances to stars using how use the orbital motion of Earth around the sun, and then you can with respect to the background sources which are far away like quasars, you can find out what is the distance of if you can measure the angle between them, where the tan theta is taken as theta itself because the angles are very small, right? So Gaia is one of the satellites which has done astrometry of billions of stars. Data is available. If you want to do anything, you can actually download and do if you have a powerful computer and some idea how to do it. Now using stellar parallax, you can actually calculate what is the distance. Distance scales are very important because unless you know the distance, you will not have any idea about the flux that is emitted by the source, right? The luminosity or the power which is given out. I hope you know about the magnitudes. It goes in logarithmic scale. So if there is a difference of, so one is 6 magnitude, one is 1 magnitude, 5 magnitudes, so it's basically 100 times yeah. And luminosity is basically given by L by 4 pi r square, or the flux that is coming from the stellar surface. Okay, any object, a spherical one, if it is coming, you say L by 4 pi r square, where r is the radius of the object, and if r is the distance to the source, then the flux is given by L by 4 pi r square. So you see, as the distance increases, there is a dilution of the flux happening, which is square of the distance that to that source, right? So you can actually in magnitude terms, you can find the distance to a star. So basically this is the apparent magnitude, the magnitude which actually you see, right? And this is the absolute magnitude, which is basically the luminosity of the star itself. And if I take this to this side, this magnitude is like the intrinsic magnitude of the source. It gets fainter. Now when it gets fainter means the magnitude will go higher, right? So as the distance increases, this apparent magnitude will be more and more, isn't it? Now, heard about 1 Jansky, right? Now I can actually calculate what is the number of photons that is given out by 1 Jansky. It's very important in instrumentation, basically, because using CCD you are basically counting the photons that are coming, right? So you can calculate the number of photons that are emitted by 1 Jansky source at any wavelength. Okay. Now now the most important part of observation is calibration of the flux that you are getting. Okay, so normally calibration is done in two ways. One, using the Vega system. Vega is a A-type star. If it is a A-type star, what is the temperature, surface temperature? 10,000 Kelvin, right? What is the line which is the most prominent in these type of stars? H alpha, right? The Balmer line. Okay, so this is basically the the Vega spectrum. So you take the flux at various wavelengths and you can calibrate. So based on this flux, so this will be your 0 point. Okay, you can even have an absolute system. Don't worry if the terms are sticking into your mind, that itself is good enough. You can read about it. Okay. Now this is basically the Vega flux 0 points that we actually do, and then we can actually calculate the number of photons that you get from so this is the good thing about this is Vega is a 0 magnitude star, right? So if you can write, so if you have a star, now I can take the Vega, which will be minus 2.5 log f of star f of Vega, right? So if I know the flux of the Vega, I know the flux of any other star. Now what is the magnitude here for Vega? 0. So you are directly getting the magnitude of the star itself. So this is basically the calibration that you do. Okay. So okay. Now this is basically now let us say the photons are produced inside the stars, right? Then they move through the interstellar medium. As they move through the interstellar medium absorbs radiation, right? You can actually find out how the absorption is taking place, okay, using the wavelength. This is inverse of the wavelength, and how much absorption is taking place. Absorption is more as you go towards UV, ultraviolet, and as you come towards the visual and near infrared, the absorption becomes smaller and smaller. That is basically because the interstellar medium, the typical size of the absorbers are about micron, submicron, basically 0.5 micron or so. This is the kind of the dust grains that you could see in the ISM. Okay, so that means that as the light passes, so this is basically the 1 Jansky, right? 1 Jansky photon. Now you take the frequency or the flux for a 0 magnitude star, which is the flux in Jansky 3631, right? So 0 magnitude star will have a flux of 3631. Now you and the magnitude is basically, so as I said, magnitude of a star is the absolute magnitude plus phi log d by 10 plus absorption. That means if any absorption is taking place due to the medium that is present in between, your magnitude will again go fainter, right? So the intrinsic is getting fainter because of the distance and because of the interstellar extinction. So you have to take that also into account. So here see 0 magnitude and the extinction. This is the flux. So you can, after noting down this equation, you can actually write down and see, if you put it 10 here, what will be the number of photons that you are expecting. So this is the number of photons that you are expecting for a 0 magnitude star. Okay. Now as the starlight comes through the Earth's atmosphere will absorb the radiation, right? How it is absorbing, the more absorption is basically in the bluer region than in the redder region. Now you can actually find out So air mass is the least when you are looking at your zenith. Okay. Now as you go down, the air mass increases, right? So as the absorption. So if you are looking at here, the apparent magnitude will be brighter, fainter and fainter. That means the magnitude will go higher and higher as your air mass increases, right? Now what do you mean by air mass 0? Outside the atmosphere, right? So actually you, by fitting this, I can calculate what is the magnitude of the source outside the Earth's atmosphere and how much the extinction it suffers in an observatory, right? So higher you go, the absorption is lesser. That's why you have observatories at high altitudes, right? So that means you have to not only put a lambda but also an absorption term which is a function of air mass. So as the air mass increases, so you have to put that also. So you see now this was the photon for 1 Jansky, this is for photon from 0 magnitude star, and this is after adding the absorptions, absorption due to interstellar medium and absorption due to the atmosphere, right? So you have photons per second per centimeter square per angstrom. Okay. So this is basically the light gathering power. So how the light gathering increases? You increase the surface area, right? Yeah, that's all is. So this basically gives you an idea about the telescopes that are there now at present, and some of which are actually planning to be built. So this is 30-meter telescope. Okay. Indian telescopes are quite small. This is the dot, which is a 3.6-meter telescope. Okay. So this is basically, so you can see that beyond a certain size, everything is segmented. That is, they are not single mirror. They are all segments added together to form bigger apertures. Okay. Yes. So these are some of the telescopes that we have. This is in Nainital, which is 3.6-meter telescope. It will come. This is the Vainu Bappu telescope, which is a 2.3-meter telescope in Kavalur, nearby. This is Guru Shikhar. This is 1.2-meter telescope. This is 2.5-meter telescope. Now the good thing is here you can do near infrared observations. Here also, this is Hanley 2-meter telescope. You can do near infrared observation as well. So because it is quite high, you can actually push to the limit of the ultraviolet from the ground. Okay, closer to 0.3 micron. This is AstroSat, and this is the UVIT, which is these two twin telescopes, a 30-centimeter telescope on board AstroSat. This is the Vainu Bappu telescope inside. Okay, so it's a gigantic telescope. If you happen to get an opportunity, please visit us. You have to just write an email to me. So this is, it's a horseshoe, it's a single biggest horseshoe finished in India at that time. It was done in 90s. This is 1-meter telescope, again in Kavalur. This is a Carl Zeiss telescope. And of course, this is the dot. So here, you can see the mounts are different, right? And they all are inclined, isn't it? Just see, they are all inclined. That means where are they pointing to? To the North Pole, because one of the axes you are fixing so that the other can be tracked. Basically because otherwise you have to convert your, RA deck to alt azimuth. Alt azimuth is the local, right? Which is basically this one. You see here, very compact. So the advantage is that it's very compact. You don't have to have a big dome like this. This is a huge dome. Okay. These are some of the other mounts that are there. This is again in Kavalur. It's 1.3-meter telescope. Okay. So this is one of the best sites, Hawaii, where you have multiple telescopes. And you all know that we all have a telescope, right? RI basically, isn't it? You can actually calculate what is the you know, how much is the power of your, your eye. All right. So this is the space telescope. What is the size? HST? 2 meter diameter. What about JWST? 6? 6 meter, right? Okay, so main important things that that you have to remember here is the focal plane and the plate scale. Plate scale is nothing but it tells you what is the size of the sky falling onto your detector. That's all. Okay, but that will determine what is the resolution of your telescope. Basically, not going into detail. This is basically the diffraction, right? Isn't it? Yeah. Okay. So you can actually simulate the data. So there is no 12-meter telescope, but if you have a 12-meter telescope, how the galaxies would look like, or how a cluster would look like. Okay, you can actually simulate. So this is one of the satellites sent in UV, which is Galax. This is the UVIT, which is in Astrosat. Okay, now this is what I simulated in if you have a 1-meter UV telescope in space, what would, so you can see that there are these blobs, right? They all resolve down to individual sources again. Okay, so that is the advantage of having higher, so in Earth you have something called seeing, right? You have seen the dancing of the stars, basically because there's a changing in the phase. That is why your wavefront is getting disturbed, right? What happens if you go to the space? Nothing. What will be the size of the stars that you see? Diffraction limited. So in space you can have diffraction limited images, whereas on Earth you are limited with seeing, because of that they are dancing, your image size will become bigger, right? So these are like prime focus, where the light from the mirror is getting focused here. This is called the prime focus of the telescope. Then you have this you have one more mirror, secondary, Cassegrain, and this is basically the azimuth. Azimuth is like you have 3 mirrors. This has implications actually. Okay, now what is the kind of mirror that you can use? The one most important thing that you have to keep in mind is they should be mechanically stable, and they should not change its profile due to temperature. Okay, so this plot will tell you what is the best things that you can actually come up with. So this is best, right? But then silicon carbide is the best one, but making it is very difficult, right? These are some of the telescopes. This is, I think, Keck, which you have this, the multiple segmented mirror. So you can actually simulate, for example, if there is, so this is basically like primary focus. Your primary instrument is sitting at the primary focus and looking at the mirror. So you're seeing the entire mirror, right? But the moment you keep a secondary, that means something is blocking, right? So you have the spiders. These are called spiders, which are actually hanging the secondary. When you look from the Cassegrain, you see actually the mirror like this. It has implications. If you have a circular aperture, what will be the shape of the PSF of the light? Airy disk, right? So this is the star image, right? But when you are putting this with spiders, there are these spikes. What is the difference between the images that you see in HST and JWST? In HST you have 4 spikes, JWST you have 6 spikes. Just check that. It comes basically because of the way the mirrors are kept. So your PSF is highly disturbed. What this means? This means that the light is leaking from the core, right, to the wings, isn't it? So you have to worry about it, because if you are looking for fainter sources, you don't want your light to be leaking, right? So this is basically, these are simulations carried out using different types of spiders that are kept along the line. No, this is not. This is basically the optics. So you see how much light leakage is happening because of the spiders that you keep. Okay, now so you can actually simulate. So there is okay, I'll come to that. So this is basically the keck, the TMT, and the ELT. You see that the shape of the domes, they're different, right? Basically because the wind that passes through these domes should not create turbulence, because that will create additional seeing disturbance in the star. So that is why the simulations are done basically with the structure to minimize this. And this is I think you people are going to Hoskote, I guess. If you're going there, you will see all these things. So I'm not so when you're putting segments, right, they all have to mimic like a single mirror, right, isn't it? But then when you're keeping the signal, how are you making sure that they all are in phases? You can use this capacitance. What will happen when the capacitor changes its position? The area changes, right? So you can actually, by sensing that, you can keep the mirrors in phase, right? Yeah, this is basically the Hoskote facility. If you go, it will be good. Now the mirrors are coated, right? They are not, so they are coated with aluminum or silver, or what is the coating in JWST? Gold. So you see the gold has very good reflectance, right, beyond a certain wavelength. For example, say 650 nanometer, right? So JWST cannot observe in laser, whereas if you take aluminum, you can actually go entirely, right? So the coating matters, really matters. Okay, so this is JWST, and you know how much gold is used in JWST? 48 grams. That's all is needed. You can calculate what is the thickness of the coating, and what is the total area. Calculate how much, right? So this is the 3.6 meter. So once you coat, the reflectivity fades down. Then what you do? You remove that coating, and then put once again. To do that, you have to use acids basically to remove it. This is the removal process happening. I think this is me. Okay, yeah. So because of the atmospheric seeing, I said stars will they get so this is basically the stellar image in phase. So this is speckle basically, right? Now so this is the seeing measurement of regions, and this is the seeing measure in Hanley. You can see this is at Subaru telescope. Where is Subaru telescope? Hawaii, right? So this is the seeing at Hawaii, and this is seeing at Hanley. You can see Hawaii is much better, right? 0.6 arc second, whereas it is 1 arc second. So, but then it depends on what is the kind of science that you want to do. That's how you choose this is basically the adaptive optics, where ideally what you should expect a flat wavefront, right? But then the wavefront changes basically because of the distortions, right? Now if you put a flat line, where will be the the focal point? Focal points will be the red one, right? But because there is a distortion, their positions change. Now you can actually estimate how much is that positional shift, right? And if you can deform the mirror which is used for observation of these stars, deform it in the way in which the deformation of the atmosphere taking place, what will happen? The wavefront becomes straight, right? So this has to happen. So change in the wavefront is happening quite fast. So you have to do this correction very fast. So it's called the closed loop correction. Okay, basically the wavefront. This is what the Snell ratio, basically what I was talking about. The diffraction limited will be 1. Then because of leakage in the because of the spider and all, your Snell ratio will come down. So this will have implications on the limit that you can detect, right? This is another quantity which is very important. It's called Nyquist criteria. So if you have a sinusoidal wave, and if I observe, take readings at certain, say, frequency, then what I will if I don't know what is the original function, I will say this is a straight line, right? If I increase the sampling, again sinusoidal but not matching, I can do that only if it is half of the frequency of the waveform, or that you are actually looking at. So this is called the Nyquist. Basically what it means is that when you are designing your telescope, the PSF of the star has to fall on 2 detector elements. Basically minimum is the 2 pixels. Okay. This is the filter systems. So you in astronomy, you have various filter systems where you can actually look at the star, because your the SED will go like that, right? So you can actually look at what is the flux that you are getting, and then you can fix the SED on that. Okay, so silicon, the band gap of the silicon is about 1.1 electrovolt, right? So you can calculate, maybe that you can take it as an assignment, what is the wavelength till which that the energy that is required, that is minimum energy that is required for the the valence band electrons to go to the conduction band, and that's about 1.1 micron, beyond which it will not work. So you see that silicon works only up to the visible. That is where you say, okay, this is the visible, so the distinction is basically the technique that you use to detect. Beyond that, if you want to, then you have to have mercury cadmium telluride or indium antimonide. The detectors and the technology changes. I think you can read about this. I'm not going into the CCD, how the CCD work, right? It's basically the rain and the bucket example. Please read that. Okay. So basically the readout, how the readout is cleverly, if you are managing the gates, you can actually read out the things. But this has implications. For example, you're reading out from one bucket to another, right? Now if everything is not going into the second one, something is remaining, that error will creep in. That's called the readout noise, basically. Okay. So 2 types are used. One is CCD and CMOS. Can you tell me what is there in your mobile camera? Find out. Okay, and what is the pixel, number of pixel sizes? What is the size of this? You have to know that. Okay. This is, if you want to simulate the data, you can actually simulate the data using, so this is, there are a whole bunch of things that you need to worry about. Not going into details. Okay, let's say, if you are interested, we have developed something called Insist Pista. So where you can put in the size of your mirror, you can put in the spiders, you can put in the filter that you want to use, you can put in the wavelength range in which you want to observe, you can actually find out all those, that bluish, those spikes that you have seen, right? You can estimate. You put in star coordinates, it will give you how it will look like if your size is 1 meter or 2 meter, or with spider, without spider. All those things you can do with this. This we developed for this is called INSIST telescope, Indian Spectroscopic and Imaging Space Telescope. It's a proposed telescope for 1 meter UV. This is the UV detectors. They are not like the CCDs, the normal CCDs. They are actually this micro channel plates, basically. So the light comes, then it passes through these channels where the light becomes multiplied, and then you detect onto your detector. The quantum efficiency is where the photons are converted into photoelectrons. So something, your CCD detects the photons, then they generate photoelectrons, and these photoelectrons are the one which you read out, right? And that depends on the the quantum efficiency of the detector. So these are the quantum efficiency curves. So you can see that they are about 70 to 80%. So this actually gives you the operational domain of your CCD, right? Because beyond this, the quantum efficiency is so low that it won't detect the photons. So you have to choose a CCD according to your science. Suppose you are interested in this range, right? Then you will be going for this red, right? So that is so quantum efficiency is basically you put 100 photons, how many photons you are detecting, right? This is the signal to noise ratio. So signal to noise, so signal that is coming from stars is basically governed by the Poissonian statistics. What is the characteristic of Poissonian statistics? If you have n photons, then the uncertainty is root n. Okay, that is true for any number, for example, so random numbers. So if I put 100 photons, what is uncertainty in the detection? It's 10, right? Okay. So these are like the classical telescope now. It is like a jet plane, it has everything. It has a primary, instrument, which is basically a fiber. Then there are this Nasmith and another, port for keeping several instruments. This is the Cassegrain. So you have all the ports filled with instruments basically. Okay. This is basically the spectrograph. You know that your CD is a grating, right? So you can actually use that for spectra. I think you people know about spectrographs. Oh, okay. I think it's already 3. So spectrograph is basically imaging something in different wavelengths basically. So if you pass through, for example, this sun during eclipse through a grating, what will you see? You see the image of the sun in different wavelengths, and that the information that you get is basically the processes that are happening in different, but then the problem here is, what is the wavelength in which this emission is happening? You have no idea, right? Because it's quite spread. So that is why you put a slit. So what are you doing? You are taking the image of the slit basically, right? So that is how, and how slit works. So this is in in Israel. So you have basically they made these blockades, and you see the pattern that you see basically because of the motion of the things itself, right? So this is the single slit, isn't it? So turbulent here, but you see here it's like you can see, so if you increase the things, these gaps, your resolution will go up. So this is an example. So if this is the galaxy, you put a slit, basically you are looking at the central region, right? And this is the dispersion axis. So you get a spectrum of all these regions, right? So basically you put a slit, you put a star onto the slit, you take a spectrum, right? How many stars are there? Plenty, right? Just imagine, take one by one, how much it will take, right? What should be the way out? Put an IFU, that is fibers. You put several fibers which will cover the galaxy, right? The entire galaxy. Now this fiber, you take it, put it onto a slit. I know which fiber corresponds to which onto the slit. What I can get? I can get spectrum of the entire galaxy, right? Whether there is a rotation happening in the galaxy. I don't have to put slit and then take one by one. I can take it in one shot, right? I can even use multiple slits like this, right? Let me see if I can. Yeah, so this is one such instrument. All these are like actuators. Actuators mean arms which is holding the fiber. So it just moves wherever you have a star, it moves there, looks at the thing, and then take the spectrum. So yeah, but then you know, um, the plane, as the the size increases, the focal plane becomes curved. That means your actuator has to take care of that also. It's not very trivial, but it's a fantastic thing. You can even slice the image itself and send each image through grating. So this will give you a cube of data. That is every wavelength you are looking at the image. You know, this is another way of looking at things. So this is the, like you can even look at these slits. You may not be interested in all the stars which are there, right? Or all the objects, right? Suppose you are doing a redshift survey of sources, of certain selected source. Then you can actually make a sheet, mica sheet, make cuts of slits onto it, and then take it as a slit. But then every time you have to change your source, you have to change the slit itself. So the best is to use this fibers and move around, right? You can even use something called DMD. This is a digital mirror, small mirrors which can actually tilt 12 degree, and that tilt can actually send the light to spectrograph or to imager. We have made an instrument like it can do imaging as well as spectrograph. So this is another way. It's again slicing the so this is basically a small gadget which does this. It reflects the light of a certain portion to certain regions of the grating, and you can take the spectrum of the region. Okay, now the telescopes are getting bigger, the spectrographs are getting bigger. It's like this, shape of a size of a person itself. And if you look at the TMT, all these are instruments which are like double story instruments. You just imagine the spectrograph is inside one of the instruments. You see the size, it's so big that it goes, IA has a Calcutta University MTech PhD program where if you are qualified just GATE CSIR age less than 28, you're welcome. Thank you. So any questions, anything that you want to ask, you can ask. So basically you have to read, whatever terms that you have listened today, you have to read them, and and then if you have any question, you can ask. Okay. I think it will be shared. There are much more material than what I have shown. You can just go through and take my email ID. If you have any questions or anything, you can feel free to. I heard that you are second year bachelor's. Yeah, right time, because whatever you're studying is all applied in astronomy. So I think you can ask any questions. So just today, maybe I don't think you can see any stars for a month now, I think. So whenever you go back, you take this, go up, look at the stars and see the month, see where the sun is, what is the array of the stars, and get an idea about it. Okay. Yeah. So astronomy is much more fun than looking at the so what is the angle subtended by sun on the sky? Half a degree. What about moon? Why? How can you say that the relative sizes are same? That's all. Yeah. Let's have a tea.